Hi everyone, welcome to another video. We're looking at something brand new now, but it's still quite related to the things we've been looking at these past few videos relating to unit circle trigonometry. We're now going to take what we've learned so far about expanding trigonometry outside of just 180 degrees or right angle trigonometry into looking at an entire 360 degree picture. And what we are doing is establishing a couple of graphs of trigonometric functions. Now, I've just gone ahead and drawn these down here. We have a graph of y equals sine theta, a graph of y equals cos theta. Now, I've given you these right off the bat, but what we're going to be doing is we're going to relate essentially the different parts of these two graphs and looking at why they look the way they do, based on what happens to sine and cos in our unit circle that we talked about before. Now, just a little bit of housekeeping. We mentioned in our previous videos on unit circle trig that based on the right angle triangle we construct with a radius of 1, where we have y and x, we established that our y coordinate here, however far up we went, that corresponds to sine theta, and x corresponds to cos theta. Now, this is not to be confused, this y equals sine theta, with my graph up here. What we're looking at down here is what we've been doing with unit circle trig so far, where we establish x and y in terms of our trig ratios, sine theta and cos theta. And we got this because of what we looked at before with, if this is some angle theta here, my sine of this angle is going to be y over 1, which just equals to y, which is what we get here. And cos theta is x over 1, my adjacent over my hypotenuse, which then just gives me x normally. So just a little reminder of why this works, and what's happening down here is not to be confused with the graphs of my functions up here. So just a little bit of a disclaimer before we start. Now let's just eliminate all of this stuff. We'll go back to just my regular unit circle and these two things that we have mentioned here. Now, let's look at why this particular graph of sine theta, y equals sine theta, looks the way it does. Now, this is a function we can clearly see because it passes the vertical line test. For every x value, I get a unique y value. And the same with cos. This is a function because one x produces one y. This is a one-to-one relation, or in other words, a function. Now, we have this thing here, and I have here a graph on an axis which has y and theta. I'm graphing y against theta here. So I'm basically showing what happens to each of my coordinates, all of my outputs for different values of theta for sine and cos, how that would look on an actual graph. Now, enough introduction, let's just get straight into it. Now, we're looking at sine theta first, y equals sine theta. Now, we said that sine theta was my y component. So let's say we start at 0 degrees here. So I start at my origin and I draw an angle that's 0 degrees. Well, how far up in the y has it gone? Well, hasn't gone up at all. The sine of 0 here, you can check this in your calculator, gives you 0 because there is a y equals to, well, sine theta equals to opposite over hypotenuse. My hypotenuse is 1, but my opposite here, there's no actual triangle. It's 0. So sine of 0 is going to be 0. Hence why we are starting over here. Now, hopefully that's all good so far. Just a very initial thing. Now, if we draw For example, an angle theta. As my angle gets bigger, my sine ratio is going to get bigger because my hypotenuse is always going to be 1. But as I cycle through and make my theta bigger, my opposite side, my y, gets bigger as well. So as we go from here up to 90, from 0 to 90, my sine is increasing because my y component here is getting bigger. It's approaching 1. And that is exactly what we get here. So my first quadrant from 0 degrees to 90 degrees is mapped out in this graph. And it hits a maximum of 1. What happens there? Well, after that, in my second quadrant from 90 to 180 degrees, I start at 1 and my y component gets smaller until it reaches 0. So as my theta keeps getting bigger, once I start living in my second quadrant, I have my theta here. As this gets bigger, my y coordinate gets smaller. It approaches 0 again. So just clearing some of this stuff up. So starting at 1 and making its way back down to 0, that's what's happening over here. From 90 degrees until 180 degrees. Okay, now that's where it gets a little interesting. If we keep drawing here, now we said in the third quadrant, my tan is positive, my sine is negative. So my ratio gets smaller and smaller and smaller because my y coordinate, if I have some angle like this, now I'm in the negative y-axis. So if I set up my ratios, I have something negative y over 1. So my thing is getting smaller and smaller and smaller until it reaches a minimum of negative 1 down here. And that's exactly what happens in my sine graph. We keep going until we hit a minimum of negative 1. And finally in my fourth quadrant, I'm starting at negative 1. My sine theta is negative here, but it's approaching, because my sine is my y coordinate, it approaches 0 again. And that is exactly what happens here. So my sine graph basically traces out what the y coordinate does as we go around the unit circle, because we said that y corresponds to sine of theta. Now let's move on to cos. We said that cos corresponds to my x coordinate. What is my x coordinate doing as we go around the unit circle? So if I just clear this up, we're going to do the same thing just now with x instead. Okay, let's talk about what the x is doing. Let's just start again here. And let's say I have an angle theta of 0. I'm going to draw this over here. Say I have an angle of 0. Well, cos of 0, that's going to be my adjacent over my hypotenuse. Now, my hypotenuse is 1. My adjacent is, we can just say that that's 1, because this is my horizontal part. So I have 1 over 1. So at 0 degrees, my cos is 1. And I see that up here. At 0 degrees, we start off at 1 here in the cos. Now let's have a look at what happens. So our angle is going to get bigger. Let's rub out this red line. As my angle gets bigger here, if I compare my adjacent side here to my angle theta, now it's something less than 1. It's gotten a bit smaller. And as we keep going up, say this is theta, my cos, my adjacent side over 1, is getting smaller. So it gets smaller and smaller and smaller. My x-coordinate, what color did I start with here? This one. I start at 1, and then my x value gets smaller and smaller and smaller until 90 degrees, where my x-coordinate here is 0. And that's what happens here. We start at 1, we go down until we get to 0. Moving on, I'm going to move a little quicker now because hopefully we should get the idea. Now, my x-coordinate is 0, and it continues to get smaller because now we're on the negative x values here. And my ratio is going to approach, for cos, -1. Now remember, we said that sine is positive in the second quadrant, so cos is going to be negative. And that makes sense because the x value here between 90 degrees and 180 degrees, that's negative. And it's starting from 0 and getting smaller until we get to a minimum of -1. And that's exactly what we see here. Now we continue going down. It's the next color, green. We're starting at -1, and now my x continues. If we look at just the x component here, it approaches to 0. So my x goes back to 0. At 180 degrees, it's -1, and as I loop around, my x component, it's getting more and more positive until we reach 0 here. But it's still negative until we reach 0. And that makes sense because tan is positive in the third quadrant, cos is negative. So that's why on my graph, the output here is negative. I'm in the negative part of my vertical axis. And finally, now that we get here, we start at 0 again, and my thing becomes positive again and approaches 1 here. And I can see that in my graph. Now I've crossed over to 0, and I'm getting positive until I hit a maximum of 1. So this is how these two graphs work, and they're directly related to what the x and y are doing, or in other words, my sine and cos are doing, respectively, in my unit circle. These graphs map out what these two do for each angle going from 0 to 360 degrees, or in other words, a revolution around our unit circle. Now, just so we can write a couple of key ideas here, and we'll do some questions in the next video. Our trigonometric functions have a couple of features, which we're going to talk about here. The first feature is called the amplitude. The amplitude is the maximum. Now, this is a little bit of a tricky definition. The maximum displacement of the graph from a reference level. What does that mean? Well, the reference level here is basically my midpoint, or in other words, my x-axis here. This guy over here. Now, we can see that the furthest away we get from this in the positive y-axis and the negative y-axis is 1. That's what we mean by the displacement here. So the amplitude is just basically how high up and how low it goes. What are those maximum points here? A way to think about this as well is we think of my trig graphs as waves. You can kind of see here from how they look, they sort of look like waves. So if you draw waves on the beach, if we do waves like this, this is when we're at high tide, we're at low tide. And basically, waves go up and down, and they go up and down around some kind of reference midpoint level. Now that here is our x-axis. So here next to reference level, I'm going to put in brackets here, it is the x-axis. That is what we mean by amplitude. It's just the maximum and minimum values of our graph. So here, it's going to be 1 and -1. So the highest up it goes is 1, the lowest down it goes is -1. So here we say we have an amplitude of 1. Now, second thing here is that all trig graphs have what we call a period. So the period is the number of degrees taken to make one complete cycle. So basically, this is just how long it takes to make one cycle around my unit circle here. Now, we're not going to look too much into this at the moment. This is outside the scope of this course, but we'll see in later maths how this kind of changes, how we can speed up or slow down how long it takes for us to complete these graphs. Now, that speed at which the graph goes around is what we call the period, the number of degrees taken to make one complete cycle. And that's pretty much it for today. So the period here was 360 degrees because we were looking at just a regular unit circle here. But both of these graphs map out what my sine theta and cos theta do along my unit circle, or in other words, what my x and what my y do around the unit circle. And we can make links between what's happening in different parts of my graph to what is happening to x and y on the unit circle.